Welcome to The Explainer. Today, we're talking about something fundamental, something that powers pretty much all of modern computing, but it's completely invisible. We're talking about the abstract machine, the secret architect behind the code we write and the apps we use every day.
So first things first, let's get a really clear distinction down. On one hand, you've got a real machine. That's the physical stuff, the silicon, the wires, all the messy, complicated hardware sitting on your desk. But on the other hand, you have an abstract machine. And that's just an idea. It's a theoretical model, a clean and simple set of rules that defines how computation should work, without getting bogged down in any of the physical details.
So, here's our game plan for this explainer. We're going to define what these blueprints for computation actually are, and then get into why we absolutely need them. After that, we'll meet some of the rock stars of the abstract machine world, take a look under the hood at their anatomy, and see how we stack them up to build real software. And we'll wrap up by looking at what's next.
Okay, let's dive right in and get a solid grasp on this central idea. What exactly are we talking about when we say a blueprint for computation?
When you boil it all down, an abstract machine is basically a mathematical concept. It's pure logic. You give it some input, it follows a strict set of rules, and only those rules to process it, and then it gives you an output. The magic here is that it doesn't care one bit about the physical world. No circuits, no silicon, no overheating fans. Just the rules of the game. You might be thinking, okay, that's a neat theory, but why bother? Why not just work with the actual hardware we have? And that's a fair question. The answer really is all about the incredible power of thinking in abstraction.
Well, these blueprints are absolutely critical for a few huge reasons. For the theorists, they let us ask the biggest questions out there, like, what problems is it even possible for a computer to solve? Or how hard is this problem, really? For language designers, they give us a rock-solid way to define exactly what a piece of code is supposed to do. We call this its operational semantics. They're also the perfect middleman for compilers, making it way easier to turn our high-level code into something a machine can run. And of course, the whole idea of a virtual machine, think the Java virtual machine, is literally an abstract machine brought to life in software.
Okay, now for the fun part. Let's look at a few famous examples, because this is where you can really see just how powerful and versatile these ideas are.
You just can't talk about this topic without starting with the big one, the Turing machine. This is the bedrock of all of computability theory, and its design is so simple, it's almost deceptive. You've got an infinitely long tape, a little head that can read and write symbols on that tape, and a simple list of rules. That's it. And yet with just those pieces, it can simulate any algorithm you can possibly dream up. It defines the very edge of what we call computable. But here's the thing. You don't always need a machine that can do everything. Sometimes you need a specialist. Enter the Pushdown automaton. It's a much more limited model. It basically has a stack for memory, kind of like a stack of plates where you can only touch the top one. Now, it can't solve nearly as many problems as a Turing machine, but its structure is absolutely perfect for one specific, crucial job, checking the grammar and syntax of programming languages inside a compiler. And we can get even more specialized. Take the Warren Abstract Machine, or the WAM. This thing is a custom-built engine designed for one purpose, to run logic programming languages like Prolog and run them fast. So instead of generic instructions, its whole design is built around the weird things Prolog does, like unification, which is a fancy way of matching patterns, and backtracking, which is how logic programs cleverly search for answers by trying a path and backing up if it doesn't work out. So we've seen the all-powerful, the specialist, and the hyper-specialist. But what do they all have in common? What are the basic parts that make up any one of these blueprints? Let's pop the hood and take a look. Generally, you can break it down into 4 main jobs that every abstract machine has to define. First, it's got to know how to handle the basic data types. Numbers, characters, that sort of thing. Second, it needs some kind of traffic cop for sequence control to decide which instruction to run next. Third, it needs rules for data transfer, just moving information around. And finally, it has to have a system for memory management, a way to grab memory when it needs it and let it go when it's done.
Now, here's a really key distinction, whether a machine is deterministic or non-deterministic. A deterministic one is predictable. It's like following a recipe. For any given situation, there is exactly one next step, no surprises. But a non-deterministic machine is more like a choose-your-own-adventure story. From the same point, there could be multiple possible paths forward. It's a mind-bending concept in practice, but in theory, it's an incredibly powerful way to think about exploring every possible solution to a problem at once. Okay, so this isn't just a bunch of cool theory. This is actually how we build the software we use every day. These blueprints aren't just standalone ideas. They're like a set of Russian nesting dolls, all stacked on top of each other.
Modern computing is all about layers of abstraction. At the very bottom, you've got the bare metal, the physical hardware. The operating system sits on top of that, creating its own abstract machine that gives us nice things like files and processes. Then, you might have another abstract machine, like a virtual machine, running on top of the OS. And finally, way up at the top is your application, which gets to use all these convenient layers without ever having to know about the crazy complexity hidden underneath. And this quote right here just hits the nail on the head. Abstract machines are the ultimate translators. They are the bridge that lets us think and code in beautiful, high-level languages, while they do the dirty work of translating our ideas down into the gritty, low-level ones and zeros that the actual hardware understands.
So let's wrap this all up. You might be tempted to think that these ideas are just old-school computer science theory, but the truth is, they're more important and relevant right now than they've ever been.
So if you take one thing away from this, let it be this. Abstract machines are not museum pieces. They are the living, breathing language we use to invent the future of computing. Every single time someone designs a new programming language or figures out how to tackle a new kind of problem, they are thinking in terms of an abstract machine, whether they call it that or not. And that leaves us with a huge, fascinating question for the future. As we push into wild new territories like AI and quantum computing, the blueprints that got us here, well, they might not be enough to get us there. So the real question for the next generation of computer scientists is, what new abstract machines will we have to invent to truly understand and harness the power of what's coming next?